Okay, so we'll just pick things up from where we stopped last time. Looking at the brief background we gave for the course. And now we know the course itself, the information theory and coding course, is grouped into two major knowledge grounds or domains: information theory and coding. And there is this algebra or mathematical technique we just have to understand, which derives directly from Shannon's theorem relative to developing codes that can be used for information transmission over a channel with minimum probability of error. And that is the finite fields. So when we talk about the finite fields, which we also refer to as the Galois fields, we are literally talking about fields with some finite element, okay? And I'll just put a few things down. So I've mentioned that the finite field derives directly from Shannon's theorem. And we know that Shannon's theorem guarantees the existence of codes that could be used for information transmission at a rate close to the channel capacity with, say, an arbitrarily small probability of error. Okay? So the idea is, given a communication channel, a noisy one at that, noisy channel at that, we're saying that the existence of codes that could transmit information, say this is a message symbol containing the information, this contains the information, we can designate the message as the information carrier, okay? So we're saying that this particular message symbol could be transmitted over this channel based on the fact that a code could be generated or created that will be able to achieve near the capacity of this channel with minimum probability of error, such that the impact of this channel will not be able to cause sufficient or extreme distortion of that symbol. Okay? So we now want to observe the finite fields as that technique that can be used to generate these codes or design these codes or develop these codes. Okay? Is that clear? Is that clear?
Yes, sir.
Okay. So now I would love to mention that one of the fundamental goals of finite fields, or better still, the algebraic coding theory, is to devise the methods for the construction of error detection and correction codes. Okay? So this now, the finite fields, as we know, is an algebraic coding theory is used to devise methods like construct error correction and error detection codes. Okay, so that's why we are really interested in this algebra, okay? Because we want to know how to construct some of these codes. And we know we have linear codes, convolutional codes, turbo codes, and the likes. But the bottom line is this message symbol cannot be transmitted the way it is over this channel without first encoding it into another length of symbols. Okay? So it means that there is another combination of symbols that will be added to these message symbols to create that level of immunity. Okay? And the approach to that requires some mathematical basis. And the mathematical basis that applies is the finite fields theory, okay? Which we also call the Galois field, okay? Okay. Now, I love us to be a little interactive this morning, okay? Who can recall the fundamental problem of information communication? What is the fundamental problem of information communication? So I need you to help us out now. What comes to mind as the fundamental problem of information communication? I'm talking to experts in the communication field, right? So you can unmute and let us know.
Good morning, sir. Interference, sir.
Okay.
Which you know generally knows noise. Yeah.
Interference. Okay. And you mentioned noise. So I want us to know now, interference and noise, are they the same thing?
No, they are different.
So,
Okay,
They are
because
different.
that caught my attention. So because you just mentioned interference, which we could also call noise. Okay, so if they are different, what is the difference?
Okay, so interference is the jamming of another signal, while noise could be, say, an addition of, say, an external force.
Okay, an
So
addition.
interference occurs when, say, probably two signals are probably meeting together at, say, the same frequency or close frequency band.
Okay.
And actually, I think interference also lead to producing noise.
Okay,
Because
interference
the
produces noise.
noise because of the frequencies, two frequencies meeting at as in points. And so that leads to producing noise.
Okay, so if I got you correctly, one said jamming, right? Jamming, J. One said jamming, right? And then another said noise can cause interference, right? Is that what you said?
So noise is produced from being as an interference.
Noise is produced from interference, right? Okay.
yeah.
Okay, noise is produced from interference. Yes, I understand interference could cause noise, but is noise necessarily produced from interference? Did you get that question?
Yes, Doc.
Yes.
We can say that one of the causes of noise is interference. So not necessarily only interference. There could be other causes of
So,
noise.
okay, so is noise a subset of interference, or is interference a subset of noise?
Noise is subset of interference.
Okay.
Noise is a subset of interference.
Okay, I think it's the other way around, that interference is a subset of noise. Because just like you said, interference is more like jamming when two or more signals interact, right? Isn't it?
Yes. Yes.
Yes, sir.
Yes, sir.
Mhm. But noise in the strict sense is some random signal, right? It's random. So if it's random, this may not be man-made, but interference usually is man-made. And when we have quite a number of signals interfering, it causes noise. That is why in practical systems, we talk in terms of multi-part distribution of signals, and meaning multiple components of signal moving or being transmitted or propagated within the channel, right? So it means that we have copies of frequencies, right? Because channel can also be interpreted in terms of frequencies, right? So when we say channel is equally the same as frequency or bandwidth. So we just have quite a number of terms. Okay, so at what point do we say channel or frequency or bandwidth? Okay, but the bottom line is all of these you are seeing moving in this channel are just some kind of frequencies. Okay, multiple copies. And the fact that they interact now makes the channel noisy. Okay? But noise as it is some kind of random electrical signal. And this could come from either natural sources or they could be man-made. So when it is man-made, then we say, well, that is interference. So noise is more like a broader representation of what is happening, while interference is just one subset of those concepts or happenings that could cause noise. Is that clear?
Yes, sir.
Okay. Okay. So if that is clear, what then is the fundamental problem of information communication? Now, I want you to underline the word information. I have not mentioned signal communication. Okay? Because I want us to begin to talk in context. Okay? Fine. Interference and the likes forms a big problem when we have to deal with the communication system. But when we now have to consider the information itself, interference is a problem. Yes. Noise is a problem. But what can we say is the fundamental problem?
Like sending and receiving, that is encoding and decoding.
Okay, encoding and decoding. can we say encoding and decoding is a solution to the problem?
Yes.
Not really.
Yes, it's a solution,
Okay, yeah,
sir.
Yes, sir.
yeah.
Yes.
Okay. Now, if encoding and decoding is a solution to the problem, then what is the problem?
I
Okay.
think the problem, sir, is the transmission.
Yes, reliable transmission is the problem. We want to achieve reliable transmission. This is the problem of information communication. Okay, as a problem of information communication. Not integrated circuit, please. Information communication, I see. Okay, now, if the fundamental problem of information communication is reliable transmission, for which you already mentioned that having effective and efficient coding and decoding scheme over this noisy channel will solve that problem, then finite string of symbols that are elements of some finite alphabet may be used to transmit the message. Okay? Now, it means that if this is what we want to address, for us to be able to address this, then what we are saying is that we can actually use finite string of symbols that are elements of some finite alphabet to transmit the message. The message. So if this is our goal, to enforce efficient and effective coding and decoding, then we are not saying that coding and decoding can only be achieved by transmitting this information using some finite string of symbols that are elements of some finite alphabet. And we are not saying that that alphabet is what we call the finite field. This alphabet is what we call the finite field. The alphabet is called the finite field. So when we talk about reliable transmission, then what should come to mind is finite fields. Does that make sense? I need your feedback.
Yeah, that means
Okay. So now, if that makes sense, I now have another question for us. So we've been able to address one major milestone, that is, for reliable transmission, we need finite fields, right? We need finite fields. It means we need codes, and these codes must be of finite duration, right? So that we are able to tell this is the length of what we are transmitting. So we know the length of what we expect to receive, right? In a certain order. So if we are transmitting some symbols, say M1, M2, all M3, all to MK, if we are transmitting this, having coded it with, say, B, N, take -1 or +1, or to, no, K, this is K, up to BN, for instance, then we can as well conclude from this description where this is k plus 1, yeah, the parity bit. Now, if we transmit this, we'll observe that this particular string of finite elements is of duration n, okay, which we will call the block length. So if we're able to transmit this, it is ordered. Now here, we have been able to separate the message bits from the parity bit, as you call it, parity bit. We could call it redundant bit. It has quite a number of names. They all mean the same thing, bits, or we could call it control bits, okay? Okay, because this is what guarantees error detection and correction. Error, let's just group it as error control. So the redundant bits or the parity bits or the control bits are what guarantees error control, because they do not include, they do not contain the information, but they are used to protect the bits carrying the information. Okay, so it means that if we are able to now represent what we want to transmit with some finite string of elements having a finite duration, say n being the block length, from the transmitter, it means we have encoded what we want to transmit. So technically, in the receiver, we should also expect a block length n when we want to decode. Okay? Does that make sense? So if we now have to also expect a finite duration of some sequence of alphabets at the point of decoding this information, then what we are dealing with in general is some finite elements which forms finite field. Okay? So that to enforce reliable transmission, we need coding. And for us to be able to code the algebra for the construction of those codes that will be able to guarantee reliable transmission is the finite fields theory. Is that clear? Because I need us to build this background.
Please, sir, can you take that again? I didn't get that.
Okay, what exactly didn't you get?
On the finite elements.
Okay.
You're saying it forms finite.
Okay, now these are the elements, right? M1, M2, M3, MK. So here we assume that these are the message bits that contains the information. Why we have B, K plus 1 up to N, because if this is length K, that's the message bit. Let's use another color. If this message bit is of length K, then this control bit is of length N minus K, because the total length is N, and this N is what we call the code word. So you now see that the length of this code word is not arbitrarily long, extending to infinity. No, it is less than infinity. It's finite. Is that clear? So what we are saying is that the alphabet or the sequence or the string of symbols is finite. That is, the string of symbols used to represent what we want to transmit is of finite duration. So we have finite number of elements which we encode. So this finite number of elements forms the finite field. Okay? So it means that we now have a domain where we say the elements are within this domain. It's more like a set. We now have a set for which the elements we are going to use for transmission are included in that set. So if we receive any symbol that is outside that set, then we know there is a problem. Is that okay? So if, for instance, I have A, B, C, D, F, and K in this set, you know, you did set theory. So we are going to be applying that again, okay? So what we are going to be doing is more of that, you know? So if we have this, and then I decided to transmit with, say, a subset of this, say A, B, C. Okay? So this is what I decided to use for my transmission. So it means that this ABC is a subset of the larger set that we can use for transmission, for instance. And both of them are of finite duration.
Oh, yes.
Now, if, for instance, I now receive A, B, C, M, what can we say about what we have received?
There is noise.
Yeah, because
There's an error.
Because M is not in the finite field of elements that we have used. So technically, we can detect there is a problem. But what if I receive A, B, C, K? What will happen here?
We can say it's error-free since K
Yes, the transmission is
represents finite field.
reliable.
Yeah, it's reliable, but
Yes,
is there an error in what I received?
no.
Based on the fact that this is the subset I use for my transmission.
Yes, since there's an additional value K.
But the bottom line is this K is also an element of
Yes.
the set, right? So my system may confuse this process to say, well, there is no error.
Yes.
But with my coding algorithm, if in my coding algorithm, I have already given the instruction that, well, whatsoever I'm transmitting is of length 3, then it's going to know that, oh, I'm receiving length 4, although everything here is correct, seems to be correct. I can build intelligence based on the finite field I have. This is my finite field. Okay? So that is where we now need coding, error control. So I can either evoke forward error, control, or automatic repeat request and say, well, since I received a bit string of length 4 against length 3, can you please retransmit? Okay. And then, or better still, I now use the algorithm running in my decoder to now map this over the structure of this to now say, well, we have the possibility of A, B, C. We don't have A, B, K. CK. So we can have ABB, we can have ACB. So we have so many options, possible options from this, right?
Yes,
Up
sir.
to yeah, we can map that. We can do the permutation or combination of this, okay? But now, by the time I do the permutation and combination, I can track that there's A, B, C. So the K is an addition which we can knock off. So the algorithm in my decoder, which is the same as the algorithm in my transmitter or encoder, will now be able to map this bit string with the possible bit strings that can be received for this communication process. And then it will correct for this. This is how the algorithm works. But as we move further, you see that it uses the parity check matrix for all of those corrections, why it uses the generator matrix for the generation of this code was. But we have not gotten to that part yet. But what I want you to understand is that the finite field contains the finite elements that are used for coding. So the idea about getting a code is to understand the finite field theory. So, madam, I don't know if you got that right. Did we just clear, is
Yes,
there clarity?
it's very clear, sir.
Okay. So now we have another interesting part we want to address now. Okay. So let's clear this. So we've handled for reliable transmission in terms of addressing the problem of information communication. So now the next question I want to ask us is, what is the fundamental problem of coding theory? What's the fundamental problem of coding theory? Now, we have addressed the fundamental problem of information communication, which is reliable transmission, right? And we have been able to establish that for us to achieve that, we need some kind of finite fields to achieve that reliable transmission, which leads to coding, right? So we need codes that can be developed from some finite field to be used for transmission over this channel. Then what is the fundamental problem of the coding theory itself? Now that we can use the finite fields to generate or construct codes, right? So what can we say is the fundamental problem of coding theory?
I can say is data compression.
Okay, beautiful. Data compression. And what else again?
Error detection.
Error detection.
So what about trade-offs?
Trade-off.
Yes,
Trade-off between what and what?
between the performance and
Okay.
the constraints.
Trade-off between the performance and constraints. And what constraints are we looking at? Because so many things.
That is the limited that's the limited computational power or bandwidth or
Okay.
maybe memory
Okay.
resources.
Okay. Talking about bandwidth, power, and other resources, right? Okay. Perfect. Good. Now, these are problems in general that we have to deal with when we now have to talk about decoding theory. And what is the essence? What are we trying to arrive at? Okay, why should we do compression? Why should we do detection? Why should we worry about the bandwidth requirement or the transmission power requirement? Why should we be bothered about some other interesting resources in terms of the signal to noise ratio, the bit error rate, and all of that? Why should we be bothered about the performance metrics and possible constraints? Why? Why all this? So the fundamental question is why? And that is the problem.
I think for us to get the exact code to use.
To the exact code to use. Okay, for us to be able to get the exact codes to use. So we're looking at efficient and effective codes, right? So yes, that's part of it. So why do we need efficient codes?
Because of limited channel capacity.
Okay, limited channel capacity still comes here because it is related to bandwidth, right? The bandwidth requirement has something to do with the limited channel capacity, channel capacity, right? Okay, so I will just, let's go for a bailout. It's still related to reliable communication or transmission, but this time we are looking at error-free communication. So we want to ensure that the errors that occur due to the channel noise are extremely improbable. That's why we are doing this, okay? Because why are we bothered about data compression? Why are we bothered about error detection? Why? Because we know at the point of decoding what we have encoded, it should be error-free. Does that make sense? Hello?
Yeah.
Does that make sense?
Yes, sir. Yes, sir.
So now we can say that the fundamental problem of coding theory is to make the error that occur due to channel noise extremely, I'm thinking about too many things, extremely improbable, extremely improbable. So that is the fundamental problem we want to address with the coding theory. We want to ensure error-free transmission. So we want to see that the error introduced due to the channel noise, due to the channel noise, is as small as possible. So we want that noise or the probability of error to reduce or extend to zero as we transmit over the channel. And what is the possible method required to improve this transmission reliability? Now, this is it. So the method required to improve transmission reliability depends on the properties of finite fields. Okay? So if the problem of coding theory is to reduce the probability of error to some arbitrarily small value, then the method we need to improve this transmission reliability must therefore depend on the properties of finite fields, because how we are able to manipulate this alphabet that happens to be some elements of this finite field matters. Okay? Now, let's assume we have a system. And this system is defined with some metrics. We say, well, we require extreme. Okay, let me make this bigger. Let me just, I want to give an analogy. So let's say these are the requirements. For instance, we want to have a system where we are able to have people with extreme decision-making capacity. Then two, we also want that system to have high-ended sacrificial leaders. Then we want people with high level of logical thinking capacity to address problem. So now this is a system, just one system, okay? This is a system we want to design. So it could be an organization. It could be a country. It could be a nation. It could be a continent. It could be anything. But in this system, we want to have people with extreme decision-making capacity. We want people with high-ended sacrificial leadership abilities, leadership ability. Then we also want people with high level of logical thinking capacity to address problems. Now, what do you think would be the finite field? Who should be in the finite field? So this is the finite field. So I need you to think now, okay? So now this, let us put up a finite field to solve this problem. This is a finite field. So who should be here? I need you to tell me the kind of people that should be in this finite field if we must achieve this system. Now, can we have madmen here? Madmen. When I mean madmen, those that have mental health issues.
No.
Are you sure? Why shouldn't we have them? Don't you think they also have high logical thinking capacity from the river side? Or don't you feel they are equally sacrificial in the sense that they are dedicated, they are shamelessly dedicated to what they feel is right, that you feel is not right?
Their decision making might not be able to meet up with that because they don't have that capacity to decide due to their mental state.
Really? So let's take a simple case study of someone who has gone really local and now fits from the trash site. Don't you know he's able to figure out that he can find what he wants from the trash site? That is why he's there. And he gets there, he sees what you don't see, and he fits on it and it's okay. Is that not decision-making capacity? Now.
Yes, it is. It
Okay.
is.
Capacity, it is.
So
it is.
But now, why am I saying this? It depends on how you view the system.
Yes.
Because extreme decision-making capacity is vague. High-ended sacrificial leadership ability is equally vague. High level of logical thinking capacity to address problems is equally vague, because this same person who have gone local goes to someone who sells food and tells the person, can you give me that bread? I'm hungry. He knows he's hungry and is able to solve the hunger problem by requesting what he needs to satisfy his appetite from the person he sees have it. You may not have that guts to go meet someone when you are dressed in suit to say, I'm hungry, give me that bread, I don't have money. The person will throw you out. But the person does not want trouble from the madman. He will give the madman the bread and say, you can go.
Okay, yeah, that's true.
Okay, now this is information theory where everything may be right. But the point now is this. We are dealing with logic, right? So it's extreme. It depends on what we are looking at. But if, for instance, we actually need some scholars, let's say we need some professors who we feel professors, we need skilled and trained leadership experts, right? Right? I'm talking now, let's talk in terms of what we consider as sane. Not that it is sane, but we consider it to be sane, right? Because I think a philosopher once said, is it who now? I think it's Shakespeare, who said, there's nothing right or wrong, thinking makes it so, right? Okay. So let's not go in that direction, because we live in a society where values have been defined, Okay, so like they say, where there is no law, there is no sin, isn't it? So since values and morals have been defined, we now have the sense of judgment to say this is right or wrong, but someone made it so, right? Through thinking. Is that? Are we clear? Are we on the same page? Okay.
Yes, sir. Yes, sir.
So it means we need professors, we need skilled and trained leadership experts. Then we need some selfless persons, right? People that are really selfless individuals. So I don't know where we'll find them. So these are the people that must be in this subset. Okay? And now we are saying that the method required to improve transmission reliability depends on the properties of the finite field. So it means that if these now are the properties of this finite field, should we desire to get this system, once we transmit these guys, those with this capacity, into the system, no doubt we should get something close to this with some minimum error. Does that make sense?
Yeah.
Does that make sense, please? I want to be sure we are all coming
Yes,
along.
sir.
So let's take Nigeria as a country as an information theory and coding problem. So what kind of country do we desire? And who are the leaders we are feeding? So that will determine the output, right? So if the probability of error is not tending to 0, so it means something is wrong with the finite field. Does that make sense? Hello?
Yes, sir, it makes sense.
Perfect. So it now means that the code that we are going to transmit through the leadership domain or channel for this country must be such that the alphabets that forms the sequence of symbol must fall within the defined elements in the finite field. So the same applies when we have to address finance, when we have to address economy, when we have to address your personal life, when we have to address communication system. That is why information theory and coding as a study applies to all domains and field of life. Okay? Now, this is the idea I wanted to pull up before we go into some of those abstract algebra. We'll try to make it as practical as we can. Are we okay right now at this point? Are we okay? Are we good? Should we progress? Any question?
Yes, sir.
Can progress.
Okay. So now if we consider a simple communication model, for instance, say we have, okay, let's change this color. So we just want to consider a simple communication model. So let's assume we have this block having the message we want to transmit, say M sub K, and this goes into another block where we have the coded message. So let's call this C sub N since it's going to give us the code word. So the code word can go right into the transmission channel. So where we are able to feed this with noise. Then what we get at this point is the received message, right? This is what is received, which now have a component of something happening in this channel. So this channel is characterized with some error value so that the received message is now the code word plus that error value. Then once we have this, so there is need to decode it. So we are able to separate the error from it. So this now becomes the decoded message. which will now be an estimated value of what was transmitted. So we'll place a hat on it to say it is estimated. It may not necessarily be exact replica, but it may not be the exact same, but it will be a replica. Let's put it that way. Okay, so let's say this is a simplified communication system model. Okay, and now coming from that background of what we just described, so let's say this is a function f and a function g. To describe the this f will now be the coding scheme, while g will be the decoding scheme, right? So we just want to position this as a function. Okay, so now here we want to assume that the symbols of the message, the symbols, so let's put this, so we want to assume that the symbol of the message, say m sub k, and the coded message c sub n, as we have described, are all elements of the same finite field. Say F cardinal Q. Okay? So we now want to represent this finite field with some parameter F cardinal Q. Now, Q in this case tells us or gives us information about the elements. Okay? So let's look this up. So Q must be an integer. So we have the message symbol, and then we have the coded message symbol, C sub n, and we are saying that they all happen to be elements in the finite field. So we say if this is the finite field, then we have m sub k here elements, and we have c sub n elements. Okay? Because if m sub k and c sub n are not all elements of the same finite field, decoding it will become difficult after it must have been corrupted. Because this information is going to tell us the possible combinations of these symbols. So that when we receive this at the receiving end, we are going to map it with the possible combinations in this finite field to see if this duration exists. If it does not exist, then we know what was received has been corrupted. Then we now have to match it with an algorithm which must have been designed based on the information from the encoder, the generator matrix, and then that parity check matrix will now be able to map it with what was received to extract the exact information that was transmitted. Because with that, the parity check matrix or the syndrome decoding, as we will see in due time, will now be able to tell us the exact location that error occurred, and we can now map it. Take note of the fact that we are talking in binary fields. That's why binary fields happen to be the most important field when it comes to coding. Use it for your cryptography, anything that has to do with coding. Okay, so we talk in binary fields because there are two possible elements, either a 0 or a 1. So when we are coding and decoding, so it's either we flip it or we retain it. So if we receive a 0 and we know 0 and we have been able to identify that that location where we have a 0 is in error, all we need to do is to flip that 0, it becomes 1, and then we are good. So we have two options to flip through. either a true or a false. That is why the binary field is of paramount interest to us. Now, let us go on. Coming from the background, hope, well, I want to confirm something from you. Hope I'm not taking things too slowly.
No,
Not
Doc,
at
no,
all,
Doc.
sir.
You're good.
Okay.
Not at all, sir.
Okay. So I want to know if I should speed up. I'm just trying to take my time before we move into some other things. But soon we'll speed up once we are able to build the basis or the foundation. Now, if this is clear, then coding from this perspective implies that we can encode a block of K message symbols. Say, now, what does coding tell us? Now, okay, this is done with. Now, coding therefore implies that we can encode a block of K message symbols, that is M sub K, such that we have a string of M1, M2, M3, all the way to MK, such that M sub K is an element of the finite field cardinal Q into a code word. So we can map this now into a code word C1, C2, C3, all the way to Cn of n symbols, such that C sub n is also an element of the finite field with cardinal Q, such that n is greater than k, because n contains both the message bits, k, and the redundant bits, the control bits. Okay? So what we are not trying to say is that the code word in this case, which is Cn, is regarded as an n-dimensional row vector. Okay? So Cn is the same as an n-dimensional row vector in the field F cardinal Q length n. Okay? So it's F sub Q to the power of n. So we are now dealing with this code word to have length n cardinal Q. Okay? So what I have just written this way is the same as what we have been talking about. Okay? So we are not trying to expand what we have been talking about, having this expression. So the next thing to now talk about is decoding scheme. We said F, in this case, is what we know as coding scheme. So F is the coding scheme. Okay? It is a function. And this function is such that it maps F, the finite field, cardinal Q of length K to the finite field cardinal Q length N, because it's taking the message bits from length K and adding redundant bits to make it length N. Okay, that's what this function does, the coding scheme function. While G is the decoding scheme function. So if the coding scheme function maps the finite field of length K to length N, then what will decoding do? Decoding scheme will equally map or demap the finite field F cardinal Q of length N to F cardinal Q length K. So we can recover the symbol, okay? So it means that at the point of decoding what was encoded, we can now remove the redundant bits, extract the redundant bits to get the message bit. Is that clear? Is
It's
this
very
clear?
clear, sir.
Yes, sir.
Okay.
Yes, sir.
So if this is clear, let's wipe this. So we can now look up an example of a coding scheme. So for us to do this, we want to consider the message block length of M1, M2, M3 up to M sub K message symbols. This is what is encoded into, this is encoded into a code word, C sub K. And it now takes this form, M1, M2, M3, all to MK, like I mentioned earlier. So we now have the control bits, B, K plus 1, all the way to B sub N. Okay? So here, the first K symbols, all of these, are the original message bits that were transmitted. Okay? And then if this, now the total length is N, and this length is K, so that this length will be N minus K, right? So the N minus K symbols in the finite field are the redundant or control bits, okay? So when we say the N minus K symbols, we say these are the redundant because they do not contain the information, or we could call them the control symbols. Okay? Now, this type of coding scheme can be represented as H being the same as M, and then the identity matrix N minus K. So this now gives us a matrix where H, in this case, is an N minus K by N matrix with entries still in the finite field. So whatsoever we're getting must be elements in the finite field, okay? And then M is what we already know is an N minus K by K matrix, which is the message bit, and I N minus K is the identity matrix, where the diagonal have unit value, right? Identity matrix of order N minus K. So looking this up, we now see that the control symbols, all of these control symbols, are calculated from a system of equations, okay? So looking this up, the control symbols, BK plus B1, BK plus 1 all the way to BN are therefore calculated using the following system of equations. That is, H is the same as 0. Well, let me put it this way. Let's just, instead of deriving, HC transpose is the same as 0, where C is the code word. So it means that by the time we multiply the code word by the parity check matrix, because here H is the parity check matrix. And this parity check matrix, as we'll see much later, is used for syndrome decoding. That is what we use in the decoder to check if there is error or not. So by the time we multiply the code word, the transpose of the code word by the parity check matrix, if it is the same as 0, then it means there is no error in the transmitted bit sequence. But what if it is not the same as 0? Then it's going to give us a value that will tell us the location where there is an error. Is that okay? Is that okay, please? Did you get that information?
No, sir.
Okay, no. Okay, no. But did you get this? That based on all of these expressions, we have been able to see that the parity check matrix is the same as this message bit that we have that contains the information and the identity matrix. So let's assume it usually looks something like, let's assume we have this 1, 1, 1, 1, 0, 1, 1, 1, 1, for instance. These are the message bits in this matrix. So it aligns with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So this matrix now we have M, and here we have I, N minus K. Okay, so the parity check matrix is usually something like this. We are just writing in the equation form, okay? So we have this. So what we are saying is that when we multiply this, for instance, by, let's assume we receive this code word. We have 1, 2, 3, 4, 5, 6. Say 1, 0, 1, 1, 1, 1. By the time we multiply this now, by this row times this row times this row times this should be equal to 0. So it means that at the decoder have this matrix in it. And this particular matrix is the parity check matrix. It is also derived from the generator matrix, okay? Because the encoder will contain the generator matrix, which will now be the transpose of this message, what's it called now? Message bit. So let's transpose this. So this 1, 1, 1 will come 1, 1, 1. Then this 1, 0, 1, 1, 0, 1, and 1, 1, 1 again, 1, 1, 1. Okay? But for us to be able to do this properly, so this formulation is more like the inverse of that. So we have 1, 0, 0. The identity matrix comes here, 0. Don't worry about all of this. We are going to solve some problems later. I'm just trying to run through one. So the identity matrix comes that way. Then we'll not take the transpose of this. That's 1, 1, 1, 1, 0, 1, and then 1, 1, 1. So what is running in the encoder is this, and what is running in the decoder is this. Okay? So the idea is the message symbol that we use for transmission happen to be generated from this. We use this to generate this code word. So that with this, when we get there, you'll see how it is done with the polynomial and all of that. So we are able to now develop the possible bit combination that can be used to encode a particular code word, or that can be used to encode the message bits to generate that code word. So once that particular code word is received, it can equally be benchmarked by the parity check matrix. So once we multiply it by this, if truly that code word exists in this finite field, it will be equal to 0. But if it does not exist in the finite field, it will give a value other than 0. So let's assume now that this now gives us something like, instead of giving us 0, let's say it's not equal to 0, it now gives us something like 1, 1, 1. Let's put it this way. It gives us 1, 1, 1. So if it gives us 1, 1, 1, it's not 0. So I will now have to look up this. I'll now say, okay, fine, let's look this up. Where do we have 1, 1, 1? It's on the second row, right? So it means that there's an error in the second row. So I now have to look this up. So you see here, the third row rather. So we have 1, 0, 1. So it means that this one is in error. So the correct symbol should be 1, 0, 0, 1, 1, 1. So we now change this 1 to 0. So because with the syndrome decoding, we have been able to see that there is a code word received that does not exist in the finite field. Is that okay? Is that clear? I need to get your feedback. Can you unmute, please? And so that I know if we can move on. Iyanu, Ibrahim, Favor, are we clear?
Yeah, for me.
Okay. So can we move on? Blessing, Enoma, can we move on?
Yes, sir. Very clear, sir.
Okay. So
Yes, sir. We can. Yeah, clear, sir.
okay. So the idea is that the finite field contains the actual elements that we'll be considering. Okay. Perfect. Now, if this is clear, so let us now review the finite field algebra. Okay, so we'll run through because we already have something online, and we'll just run through to clear all doubts and then see if we'll be able to do that in another few minutes. So we already established that the finite field is the same as the Galois field, right? And what we know it is just the algebra of coding theory, okay? It's the algebra of coding theory, okay? Now, if we want to put it simply, like I mentioned earlier, we'll say that this finite field is a field with finite number of elements, okay? And now I have been representing it as F cardinal Q, which is equally the same as the Galois field GF with a prime value raised to the power of M. Now, this just tells us that it is a polynomial, okay, raised to the power, where M is an integer, okay? So M could be some value 2 or more, and P is a prime number. Okay, so it means that P could be 2, it could be 3, it could be 5, it can be an even number, okay? And if we take, for instance, the Galois field or the finite field 2, then it means that this is raised to the power of 1, right? Now, how about the Galois field 2 to the power of 3? So it means this is the same as the Galois field 8. So while this contains 2 elements in the finite field, this contains 8 elements in the finite field. Is that clear?
Yes, sir.
Now, and fields, the Galois field of this form, P to the M, are referred to as extension fields because they are polynomial fields, okay? While the Galois field of the other P are referred to as prime fields, okay? Okay, so now for us to have a field, it means that there are stages to this. Okay, so we have group, we have ring, we have field. Okay, so our point of emphasis is the field, largely because it is a field, largely because we can perform addition operation, subtraction operation, multiplication operation, and inversion operation. But for a ring, we can only perform addition operation, subtraction operation, and multiplication operation. While for a group, we can perform only addition and subtraction operation. So that is why we are not really interested in the group or in the ring, largely because at some point we also want to perform inversion operation when we are dealing with our codes. Is that okay? We are just building a little background. Is that clear?
Yes, sir.
It's clear, sir. It's clear, sir.
Okay.
Yes, sir. Yes, sir.
So now, but what if we have a group? We now say that a group is a set of elements also. A ring is also a set of elements. Now, a field is equally a set of elements. But the idea is that for the group, it is a set of elements in which the multiplication operation is used to combine two or more elements. So once we use that multiplication operation to combine two or more elements, the resulting element must be an element in the group for it to be a group. Okay? So since multiplication operation is performed, now there are certain key properties we must bear in mind. Okay, this will help us establish the properties for a field. Okay, so it means that this group is closed under the multiplication operation. So when we talk about closure, what we are trying to say is that if we find the product of two elements, that element also must be a subset of the element. So for instance, if for all A, B, C are elements of the group, then if for instance we say A times B times C, it should give us the same as A times B times C, and these elements or this result should also be an element of this group. So if, for instance, this gives us P, then we now find out, is P an element of this group? If it is not, then it does not form a closure. Is that clear? Did you catch that?
Yes, sir.
Okay.
Yes, sir.
Then we also say that this group, in this group, multiplication operation is associative. So when we say it's associative, we are saying for all elements A, B, C being elements of this group, then A dot, just like I wrote here, dot B dot C are elements of A, are the same as A dot B dot C. Okay? So that in this case, if this is, so let me add P here for instance. If this is equal to P, then P is also an element of G. So this forms a closure. Okay? It forms a closure. So technically, what we are trying to say for closure is that A dot B must be an element of G the same way as B dot C should also be an element of G. The same way any multiplication operation should be an element of G. Okay? And then the next point you need to also take note of here is the existence of an identity or neutral element. Okay? So in multiplication operation, 0 does not form a neutral element, but 1 forms a neutral element. In that, if 1 is an element of G, then A times 1 will be the same as 1 times A, for all A also being an element of G. Okay? So it means that there exists an identity or neutral element in G where 1 is the neutral element, okay, for multiplication operation. So there exists a neutral or an identity element in G. And also, we have the inverse operation, okay, such that A times the inverse of A should be the same as the inverse of A times A, which is the same as a neutral element, the neutral element 1. So that for every element in G, there exists an inverse of that same element in G, okay? So if the inverse of the element does not exist in that group, then it does not form a group. And also, G is commutative, such that A dot B is the same as B dot A for all elements of A, B, C being being elements of G. Okay, now this particular point is of interest to us, this inverse operation. So now let us assume, because if you recall, I said 1 is a neutral element or an identity element when we are dealing with multiplication operation. But you now see that 0 is also a neutral element when we are dealing with addition. Okay? But in this case, A dot A inverse is equal to 1, right? So 0 dot 0 inverse is not equal to 1. So when it comes to multiplication operation, 0 cannot be an element of the group because it violates the fourth condition. Does that make sense?
Yes, sir.
When we are considering multiplication operation. But if we should consider addition, for instance, then 0 is a neutral element because 0 and 1 are the neutral elements. Now, 0 will be a neutral element if we are considering addition operation for a group, in the sense that A plus A inverse, for instance, or let's not use A inverse because we are not dealing with multiplication division. That would be minus, right? A plus minus A should be equal to 0, right? So if we should consider 1 plus minus 1 is equal to 0, then if we also consider 0 plus minus 0 is also equal to 0. So 0 is an identity element or a neutral element when we are considering addition operation. Is that clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So So while we can address this as multiplicative inverse, this is additive inverse, right? Minus A. Okay, so now the field theory itself follows directly from this. So if we now have to talk about fields, let's if we now have to talk about fields, so we now say a field is a set of elements in which addition, multiplication, subtraction, inversion can be performed. But in the strict sense, subtraction is the same as addition. Hello? Did you get
Yes,
that?
sir.
So when we are performing addition and subtraction, they are the same. There's no difference in this binary field, okay? So in the finite fields, let's put it that way. So in the finite fields, you observe that addition and subtraction are the same. So when we say addition, subtraction, you perform the same operation. But multiplication, inversion vary, okay? So here, the major tools we want to consider is that addition and multiplication operations should or must be performed on the elements, and they must satisfy, or better say, addition or subtraction operation must satisfy these conditions. Now, you realize that when we talked about the group, although the multiplication operation conditions were established, there are some instances, or there were some instances as indicated, where addition operation may not apply. Okay, the case of the multiplicative inverse. Okay, 0 cannot be an element, right? Couldn't be an element. But now, for the finite field, we now see that with the addition operation, all elements, including neutral elements, 0 forms an additive group. Okay? So all elements, including the neutral or identity element 0 forms an additive group. Now, when we now consider multiplication, all elements except the neutral element 0 forms a multiplicative group, okay? So all elements except the neutral element 0 forms the multiplicative. Just like we already mentioned. So if we now have the two operations, then we have the law of distributivity, okay? Distributivity combines the two operations in the sense that we have A, B, C as elements of the finite field, then A dot B plus C will be the same as A dot B plus A dot C. Okay, so here we have both the additive and multiplicative operations. So now, just a few things to note. When we consider set of real numbers in finite fields, having neutral element 0 for the additive group, then 0 becomes the 0 element or the identity element relative to addition, okay? And for a set of real numbers in a field with neutral element 1, for all multiplicative group, 1 becomes a unity element or identity element, okay, relative to that multiplicative group, as we have mentioned, okay? And the order of the field is the same as the total number of elements in that field. So we say this is of order 8, order 9, order 10, order 2. So when we are able to tell the total number of elements in a group, then we are able to tell the order, okay? Which gives us the information about the cardinal, okay? Now, how do we perform all of these addition, subtraction when it comes to coding? And we have been able to establish that we are dealing with polynomial, but our emphasis here is on binary vector space. Okay? Because we are dealing with two elements, major elements, the 0 and 1. Okay? So this brings us to the binary digits. So how do we perform operation in the binary vector space? So let us look that up. So it's not different from what you already know. And here, we want to denote the binary vector space as V cardinal 2 of length n. Because here, n is the binary vector length. Okay? Just what you already know. So we now say that this vector space V will exist over a finite field F if the following conditions are satisfied. So this binary vector space will exist over the finite field if these conditions hold. So the first is that when alpha, for instance, is an element of this field, and then V is also an element of V, so should we take the product of alpha and V, it must also be an element of the vector space. Okay? Because the binary vector space has been mapped to the finite field. Okay? So should we have a scalar, for instance, in the finite field, multiplying an element in the binary field, whatsoever we get must be an element in the vector space. Now, this is the reason, or that is why we use the modulo addition or multiplication in the binary vector space, so that no matter what we are multiplying, the element must be present in the vector space. We are going to see how we are able to make that possible. So another condition is that if, for instance, U and V are elements of the vector space, and then A and B are elements of the finite field, then A times U plus V is going to be the same as A times U plus A times V. And also, A plus B times V will be the same as A times V plus B times V, satisfies the distributivity law. Distributivity law. And the third condition that must be satisfied is that if U is an element of V, and also A, B are all elements of the finite field, then A times B times U will be the same as A times B times U, satisfies the associativity law. And also, if 1 is an element of the finite field, then 1 times V will be the same as V for all V being element of the vector space. And you'll observe that in this case, the finite field is built up of scalars, okay? So if this is what we get based on the binary vector space. And we are saying that if, for instance, we have two elements, then 2 times 3 should also give us an element in this. So if, for instance, 2 times 3 is 6, then how can we make sure or ensure that it is also an element in this? So then we will now have to use the modulo 2. So that will be 2 divided by 3, 6 divided by 2 will give us 3 remainder 0. So the answer will be 0. And 0 is an element of the binary field where we have 0 and 1 as elements of this. So you now see that with the modulo 2 addition or multiplication, we are able to establish the fact that once we are dealing with binaries, whatsoever element we come up with either by multiplication or addition, it must be an element in that vector space. Is that clear? Hello?
Yes, sir. It's clear.
Okay.
Yes, sir.
Okay. So now, looking this up, if we have a binary vector space, V sub 2, to denote it is a binary vector space of length 2, so this means that this is 2 to the power of n. That will give us 2 to the power of 2, 4 elements. This will give us 4 elements. So it means that this vector space, the binary vector space of length 2, can have elements 0, 0, 0, 1, 1, 0, and then 1, 1. Okay? So it means that these are the possible elements in this vector space. And so should we decide to do mapping in terms of coding, these are the possible combinations we can use. Okay? Is that okay? Is that clear?
Yes, sir.
Okay. Now, let us quickly revise the modulo operation. Okay, so let's start with modulo 2. So we're going to walk through this together. So we have 0, 1 this way and 0, 1 this way. So 0 plus 0 using the modulo 2 operation. This is for modulo 2 operation or addition. So what will that give to us? 0 plus 0. So I need us to do this together. 0 plus 0 will give us what?
0.
0 plus 1?
1.
1.
Okay, so 1 plus 0?
1.
1.
1 plus 1?
1 remainder 1.
1.
Hmm? So 1 plus 1 will give us 1.
1.
It will give us 0.
Okay, so how did you get the 0?
0.
Because 1 plus
1
1
plus 1 is 2. 2 divided by 2.
It's equal
2
to
divided by 2. 1
remainder
remainder 0.
So we take the remainder. Perfect. So let us do modulo 2 multiplication. So this is going to give us the multiplication. So we have 0, 1, 0, 1. So 0 times 0. 0 times 0.
0.
0.
0 times 1.
0.
0.
1 times 0.
1.
0.
1 times 1.
1.
1.
Okay. So let us do modulo 3 multiplication. So we have mod 3, right? So we have 1, 2, 1, 2. So 1 times 1?
1.
1. 1 times 2?
2.
2 times 1?
2.
2 times 2?
1.
1. Now, do we all understand this? Is this clear?
Yes, sir.
Yes, yes.
Okay.
Yes, sir.
Okay, so let's do mod 5 multiplication. So with this, we'll be sure if it's really clear. 1, 2, 3, 4. 1, 2, 3, 4. So okay, so 1 times 1?
1.
1 times 2?
2.
1 times 3?
3.
1 times 4?
4.
2 times 1?
2.
2 times 2?
4.
2 times 3?
1.
1. 2 times 4?
The remainder
3. 3.
3.
3. Okay. 3 times 1?
3.
3 times 2?
1.
1.
3 times 3?
4.
4.
3 times 4?
4.
2.
Then 4 times 1?
4.
4.
4 times 2?
3.
3.
4 times 3?
2.
Then 4 times 4?
1.
1.
1.
Okay, that's fine.
Wow.
So that's fine. So that's pretty cool. So let us move on to the prime field. So it means when we are performing modulo addition or multiplication, we will run into issues. So we already know we are playing with the addition. So the remainder is of interest to us. So as to ensure that element is an element in that field, because in the in this field, the elements that exist ranges from 0, 1, 2, 3, 4, right? That's in base 4, in base 5. Okay. Now, we already explained that we have 2 types of finite fields, okay? Finite fields, or the Galois fields types. We've mentioned the prime field, excuse me, the prime field, and then we've also mentioned the extension field. So we said this is designated as the Galois field P, and this is designated as the Galois field P to the M. And this is prime field because all the elements are in integer form. And this is extension field because all the elements are in polynomial form, because it is to the power of m. So we can say x to the power of 2 plus x to the power of 1 plus 1 plus s to the power of 3 plus s to the power of 4 all the way, okay? So this is polynomial form. Okay. Now, in considering these fields, we have the field that is of interest to us in coding, which is the Galois field 2 to the m. Okay? Now, because this field contains 2 elements in the polynomial form, so we can either play with a 0 or 1 in that string, okay? In that, in the polynomial form. And now, another thing I'd love you to pick from here is that we can actually perform all of the regular arithmetic we just played with in the modulo form. Okay? And I already mentioned that addition and subtraction are the same. Okay? So we can now look up how addition, subtraction, multiplication, and inversion is performed in the finite field. We already know it is a finite field because we can perform addition, subtraction, multiplication, and inversion. Okay. So in your previous note, you could look up the basic definition, okay, whereby we talk about the addition operation of two elements, okay? These are polynomials. So the fact that it is a polynomial, it means that it exists as a to the n minus 1, s to the n minus 1, plus all the way to a sub 2 s squared plus a sub 1 x plus a naught, okay? Such that this polynomial is an element of the Galois field 2 to the n, okay? And now that we have something like this, you will now observe that all of these coefficients, a, n minus 1, all the way to a2, a1, then a naught, assume values between 0 and 1, okay? So it means that all the coefficients, a sub I, are all elements of the Galois field 2, for which we have just 0 and 1 as the element, okay? But when we scale up to the extension field 2 to the m, we can have more elements in the finite field, okay? So for the prime field, having 2 elements, we see that all of these coefficients of the polynomial can either be a 0 or a 1. Is that clear?
Sorry, what is it, sir? I didn't get that.
Now, you know, we are now dealing with polynomials, right?
Okay.
So the elements in the finite field can be described as polynomials if we are dealing with extension fields. And we mentioned that in coding in general plays with the extension fields, which is g of f 2 to the m. Okay? Now, we know that what we have here tells us the number of elements.
Yeah.
So if, for instance, we have the finite field 2 to 2, so this is going to give us 4 elements. What about if we have 2 to the 4, this is going to give us 16 elements. Now, the finite field 2 to the 3 will give us 8 elements. Okay, so depending on our code book, let's put it that way. So we want to develop a coding scheme, and now we must tell the size of our code book, which we are going to use for encoding to tell the number of code words. So if I use a code book of size 2 to the 2, that is going to be 4. So it means that I have the possible bit combination of 0, 1, 0, 1. So this will form the possible combination for my code book. So should I add redundant bits to this, then it means that in my encoding system, I have 4 possible combinations. Is that okay? So it means that my decoder is also going to have this. Recall, we're not going to use this as my generator matrix at the encoding point, while at the decoding point, we will, now have to come up with the matrix for the parity check to decode. So bear these things in mind. So let's not forget, let's not get carried away with this citing mathematical jargon, okay? Let's still retain the fact that we are doing this because we want to encode and decode, okay? So how large do I want my code book to be? So do I want my code book to contain 16 possible code words to play with, so that if I have to decode, we will not have to look at that code book to be sure that, oh, these 16 possible code words here, do they exist in the code book? If it's yes, then extract it, then put the information together. What was mapped to it? Oh, he said hello. That was what he said. Good. Now, if we can't find it in it, then we have to do some operation, either modulo 2 multiplication or addition, to now see the remainder. And once we find the remainder, we'll now go back to the code book. Is that in the code book? If it says yes, then that is what was transmitted, only that it was corrupted. Does that make sense?
Yes, sir.
Okay.
Yes, sir.
So let us look at one example. So as we begin to look up these examples, then I think things will get clearer. So let us look at the Galois field 2 to the 4. So we know that looking up the polynomial spread, we already described the polynomial spread for the Galois field P to the M. And we said this is the same as AM minus 1, SM minus 1 plus all the way to plus A2x squared plus A sub 1x plus A naught, right? So that's the polynomial spread. So what's going to be the polynomial spread for this? So this is to the 4. So M in this case is 4. So that will be 4 minus 1. That will be A3, right?
X3.
3
X
plus A2
X2.
x squared plus A1
A1
x plus A
plus A.
naught. So this is A naught x naught. So x to the power of 0, anything to the power of 0 is 1, right? So that's how we got that. Okay, so we don't need to present that. Okay, so we have described the polynomial. So how are we now going to generate the code words? And recall that here we have 4 coefficients, right? Now, we said, now let us map these two. We said these coefficients, AM minus 1, all the way to A sub 2, A sub 1, A sub naught, assume values from 0 and 1 because we are in the binary field of length M, right? Right? So this is not outside the binary field. If P was some number other than 2, then a prime number other than 2, then we won't be in the binary field. Let's say P was 3, you know, or was 5, but it's 2. So we're in the binary field. So the vector space is 3. But now, remember our vector space is of length n. So we're able to tell is binary sub 2, right? So this length now is equal to 4. So what will be the coefficient? So it means we now have 4 coefficients for this. So for the Galois field 2 to the 4, we have A3, A2, A1, A naught. Is that clear?
Yes, sir.
Okay, so now if this is clear, we know that these coefficients can only take on values from either 0 or 1. So how are we now going to map that relative to our, what's it called now? To our polynomial. So I'm going to wipe this because I'm going to need some space. We just place this for illustration, right? So we don't need this anymore. Now I'm also going to wipe this so that now we have our coefficients, 4 coefficients, which are A3, A2, A1, A0. And now we know that for this vector space 4, we have 2 to the 4, 16 possible elements. Okay? So it means that we can literally describe these coefficients, A3, A2, A1, A0, and use that to develop our polynomial. And we know we have 16 possible, so this would be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right?
Yes.
Isn't it? Good. So now,
Yeah.
Now when they are all turned off, so we have all zeros, right? 0, 0, 0, 0. So if we have 1, then it means this is turned on, right? This 1, 0, 0. And if it's 2, so it means this is turned on, 0, 0. Isn't it?
Yeah.
Now if it is 3, this is 1,
0,
1,
0.
0,
1,
0.
0.
Now if it is 4, this 1, 0, 0.
0, 0.
Now
Zero.
if it is 5,
5 is
if it is 5,
Oh,
this is 1,
1,
1,
0,
1, 0, 1.
1,
0.
0. If it is 6, 1, 1, 1.
0.
So if it is are
That
we
111 is 7.
I think that one is 0, 1, 0,
yeah.
1.
So this is are we doing something wrongly yet? I think we are in
Yeah,
order.
second to the last. Second to the last is not
Second to the
seven.
last.
Second to the last is
This is 0, 1, 2, 3, 4. This is
To the 101.
101.
okay, this is 101, right? That's
Yes, sir.
5, yeah. Yeah, that's where we got things screwed up. 101. So then this
110.
that'll be
110. Yes.
0. So that's 4 plus 2. That's 6. Then 7 will now be 1, 1, 1, 0. Right? So then the next now is 8, 1, 0,
0, 0, 0.
0.
9, 1, 0,
1, 0, 0, 1.
and that's
1, 1,
0,
0, 1, 0.
10. Yes.
and 1,
10.
0,
1 1.
1.
1, 1.
And this will be 1,
1,
1,
1,
0, 0.
So this will be 1,
1,
1,
1,
1,
0, 1.
1.
and this will be 1, 1,
1, 1, 1, 0.
1, 1, 1, 1.
1.
Okay, so these are the 16 possible elements. So from this, we can map to our polynomial to say that our polynomial 2 to the 4 contains, the first is all 0, right? So all these coefficients are 0, so that reduces to 0 as our first element. So now the next is 1, only this one is turned on, so A3, A2, A1 is all 0, so we have 1, right?
Yeah.
Because the coefficient is 1, A0 is 1, right? Is that clear?
Yes.
So the next is, this is 0, this is 0, but A1 is 1 times x, so this is x, right? Because this is 0. So we've taken care of this, taken care of this, taken care of this. So now A3 is 0, A3 is 0, but A1 is 1, A0 is 1. So that would be x plus 1, right? Is that clear? That's for this. Is that clear?
Yeah.
Yeah, because this is 1. 1 times x is x plus 1. A0 is 1, right? So the next now is this. Only A2 is 1. So that's x squared, right? Is that clear?
Yeah. Yeah.
So now the next,
X squared plus x.
x squared plus x. Perfect. So just tell me the polynomial. You already know how it works. So then the next will be what? X squared plus x plus 1.
Plus 1.
Then the next one is x cubed, right? X cubed, right?
Yeah. X cubed plus 1.
X cubed plus 1. Then the
X
next
cubed plus x
plus x. X cubed plus x
plus x plus 1.
X cubed plus x squared.
X
X
cubed
cubed plus x squared plus 1.
X cubed
X cubed plus x squared plus
x. Then x cubed
plus
x squared
plus
x plus 1.
Plus 1.
Now, these are the 16 elements in this extension field. Okay? So now, what if we perform some operation on these elements? So you can as well do the same for the Galois field 2 to the 3, right? It's simple. And you observe that all the elements there are 0, 1, x plus 1, x squared plus 1, x squared plus x, and then x squared plus x plus 1. 8 elements from the same principle, right? Now,
Yes, sir.
Now, if we decide to perform addition or multiplication operation, now the encoding scheme already have these elements in this extension field. So after mapping, and if it realizes that the final element is not an element in this field, it knows there is a problem. So it will now have to perform a modulo 2 addition or multiplication to now check for the remainder to see if that is also an element. And if there is not, then there's a problem again. So let us take an example from this. So let's say we have 2 elements, x cubed plus x squared plus x plus 1. And then the second element is x cubed plus x squared plus 1. So let us add this up. Now, we add their coefficient. The coefficient of this is 1 plus 1, x cubed, right? Plus 1 plus 1, x squared, plus x plus 0 is x. Then plus 1 plus 1. So these are all modulo 2 addition, right? So 1 plus 1 is what? Is 0. So this is going to give us 0 times x cubed plus 0 times x squared plus x plus 0. So the answer is x, right? So we just added 2 polynomials, phi 1 of x and phi 2 of x. Okay, so these are 2 polynomials. And now, these polynomials, we picked, now this is 1, and then the other one is this. So these 2 polynomials are elements of this extension field. Now, after addition, we got x. X is also an element in this field. Did you get that?
Yeah.
Yes.
So let us now perform multiplication. That is where things may really get messy sometimes. Okay, So because by the time we perform multiplication, we now see, okay, is this element also in this system? So this will take us to irreducible polynomial. So let us wipe this. Let's wipe this. And then let us assume we now have to multiply two polynomials, x cubed plus x squared plus x plus 1 times x cubed plus x squared plus 1. So what are we going to get? We get s to the power of 6, this times this, plus s to the power of 5, this times this, plus s to the power of 4. Yeah. This times this, s to the power of 4, plus x cubed. So this times this, right? We are done with that. So plus x squared times this, that's x to the power of 5, plus this times this, s to the power of 4, plus s cubed. So this times this plus x squared, right? So 1 times this, x cubed plus x squared plus x plus 1, right? So let us collect like terms. So this will be x to the power of 6. So s5, we have s5 here, s5 here. So that would be plus 1 plus 1, s to the 5, right? So we have taken care of this, all right? So is there any other? So the next is s4. How many do we have? We have 2 of it. So that will be another 1, 2 addition 1, s to the 4. So we've taken care of this. So come to x cubed. So how many x cubed do we have? We have 1, 2, 3. So that'll be plus 1 plus 1 plus 1 x cubed, right? So we've taken care of all the x cubed. Then plus s squared. We have 2 of it. 1 plus 1 x squared. That's this. Then plus x. 1. Now, this 1 plus 1 is 0, so it means we have x to the 6 plus 0 times x to the 5 plus 0 times s to the 4 plus 1 plus 1, 0 plus 1, 1. 1 times x cubed plus 0 times s squared plus x plus 1. So this is taken care of. So what we have is x to the power of 6 plus x cubed plus x plus 1. So this is what we got as our final code or the code word. Now let us look up our polynomial. Now x cubed plus s squared plus x plus 1 is an element here. S cubed plus s squared plus 1 is an element here, but x to the 6 plus s cubed plus x plus 1 is not an element here. So it means there's a problem, right? Is that now? Do you see where the problem begins? Yeah. So now, now that you have seen that this element is not in the field or the polynomial field, which stops somewhere around here, then we will now have to use what we call the irreducible polynomial to divide this. Okay? And then the remainder has to be an element in this field. Okay?
Hello, Doc.
Yeah, go ahead, please.
Okay, yeah. I just want to be sure because these two polynomials that you've chosen to multiply, you just chose two of them randomly. If I choose another two combination, I'm going to have a polynomial that will be in that field.
That's fine. That's fine. So it means our analysis stops there. So it means the element is in the field. But now that we have discovered that the element is not in the field, because we need to show you that when the element is not in the field, then there's another mathematical operation we perform on that element. which such that we now have to do long division. So it means that this element will have to be divided by an irreducible polynomial. So we have some polynomial in our study that we refer to as irreducible polynomial, because those are polynomials that cannot be factored into the product of two or more non-constant polynomials over the given field. Okay, so we will detail them. Okay, I know I didn't provide the details in the previous video, so we'll provide the details now. So we know the possible irreducible polynomial that can be considered in specific fields. Okay, so now that we have done this, we now have to define that irreducible polynomial. Now, I would not want to bore you with that definition, which you have in your other notes. So let us assume one irreducible polynomial, okay? And that is this. So I want to take this. I'm going to provide a list of irreducible polynomials, so don't worry. X to the 5 plus x squared plus 1. So this is an irreducible polynomial. So if we should take this, what we're trying to say is that we have to divide this by this, and then whatsoever the outcome is will be the resultant effect. So let's wipe this so we don't lose track of this record.
Sir, before you go further, how did you get the irreducible polynomial?
Yeah, that's why I said we are going to come to that. Okay. So
okay,
yeah, we'll come to that. So I will specify them. It's just that they cannot be factored beyond what it is now. So I'll come to them. Don't worry. So this is what we have, right? And this is one irreducible polynomial. So what we now want to do is that we want to do a long division, x to the 6 plus x cubed plus x plus 1. We want to divide by this irreducible polynomial, s to the 5 plus x squared plus 1. Okay, we want to perform long division. So I think we can wipe this out, for instance. So depending on the irreducible polynomial we adopt, we are going to get a different result or a different element. Okay, so if x to the 5 goes into this, s to the 6, so it can go into it how many times? Just one time, x. So that will be x times x to the 5. That will be x to the 6, right? S times this plus x cubed plus x. So once we perform addition or subtraction, in this case, this reduces to 0, 0, 0. So the final outcome is 1. And we take the remainder, isn't it? So it means we check. So that element is here. Okay? So this irreducible polynomial is very, very useful in coding theory. So we are going to tell, because we use them in cryptography, we use them in error correction codes, and we also use them in random number generation, okay? They are very, very vital. So when we perform operation and all of that, there are specific sets of irreducible polynomial that can be applied in our algorithm to get what we want, okay? So let us try another irreducible polynomial, say x to the 4 plus x plus 1, okay? So we have x to the 6 plus x cubed, I'm coming, x cubed plus x plus 1. So x to the 4 can go into this x squared, right? So x squared times this, that's x to the 6. S squared times x, that's x cubed, then plus x squared, so x squared. So we don't have x squared here. So now, what do we get? This reduces to 0, this reduces to 0, so we have x squared plus x plus 1. So this is the remainder. So do we have s squared plus x plus 1?
Yeah.
Yeah. So this is an element. So now, what if we use any random polynomial to perform this long division? The chances that we will get an element in this field will be slim. Okay? So the interesting thing about this is that regardless of the exact or the particular irreducible polynomial we use, the chances that we will get an element in that field is high. Okay, because what are irreducible polynomials? Okay, let's just talk about that before we move on. So, like I already mentioned, now when we say irreducible polynomial, we mean that this is a polynomial that cannot be factored into the product of two or more non-constant polynomials over a given field. So the field in this case is the Galois field, okay? And these polynomials are essential for constructing the extension fields, okay? Elements in the extension fields. And we can talk about the properties, okay? They have degree m, they are primitive polynomials and all of that. And we can now give some notable examples, okay? So when we talk about the binary fields, for instance, so irreducible polynomials in the binary field. So we have x plus 1, we have x squared plus x plus 1, we have x cubed plus x plus 1, we have x cubed plus x squared plus 1, we have x to the 4 plus x plus 1, we have s to the 5 plus x squared plus 1, we have s to the 5 plus x cubed plus 1, and we have x to the 6 plus x plus 1. Okay? Now, what about the ternary field? We have x plus 2, x squared plus x plus 2. We have x cubed plus x plus 2. Then we have x cubed plus 2x squared plus 1. And then in the quinary field, we have x plus 2, x squared plus 2x plus 3, and then x cubed plus 3x plus 2, and x to the 4 plus x squared plus 2. So these are possible irreducible polynomials by standard that could be adopted. And we use these irreducible polynomials in cryptography, you know, because they are used in algorithms like the advanced encryption standard, you know, where the extension field 2 to the 8 arithmetic is common, okay, in this case. When you are doing cryptography, probably you are into cybersecurity and all of that. Now, in error correction codes, they are used for the construction of Rich-Solomon code and BCH codes because those codes rely on irreducible polynomial, even random number generation. You know, the linear feedback shift registers, they use irreducible polynomials, okay? So I think this is a good place to stop. The only thing I haven't mentioned is the inversion in Galois field. So there's an algorithm that is used, which is the extended Euclidean algorithm. So we may not be able to apply that analytically, so you run computer programs on that, okay? So, okay, I think you spare me just 1 minute or two I just want to take a walk, then I'll come back to take some questions, then we'll move on. Is that okay?
All right, sir.
Yes, sir.
Yes, sir.
Let us start our lecture.
All right.
Okay, so can we pick things up from where we stopped?
Yes, sir.
Okay, yeah, thank you so much. So, yes, so on this, I'll say, well, we've been able to run through quickly specific details about the finite fields. So, do we have any question before we move on? Any question, please? Okay, so I need to hear from you, please. Feedback. I can see Joel, Ianu. I haven't heard their voices in this class. Ezekiel, Favor, Ibrahim.
No question from me, sir.
Okay.
Yes, sir.
We have Taiwo, we have BLVCK.
No question from here either.
So, can we say all that we've talked about so far is clear? Can we say it's clear? Everything we've talked about so far, is it clear?
Yes, to an extent, sir. The explanation is very, very wonderful for me. So I need to just go back and revisit and familiarize myself with the concepts.
Okay, that sounds
Yes, sir.
good. So if that's what it is, so it means that now that we've talked about the finite fields, so what comes to mind is error correction codes. So we want to be able to use this technique to construct error correction codes. And we have two broad categories, although more than that. So we already know we have the block codes, we have the convolution codes, and then we are going to add another interesting type, the turbo codes. Now, in most of your emerging technologies, your 3G, 4G, 5G, and the likes, they actually apply turbo codes, while the legacy technologies apply convolution codes. For some obvious reasons, we are going to document in this course, okay? So now we are going to begin our interaction in terms of detailing how these codes are designed and developed, okay? From the linear block codes, which are about the simplest and basic linear block codes. And then we'll talk about a specialized class of these linear block codes, the cyclic codes. And then look up their applications, and then see how the encoding and decoding is achieved. So at the point of encoding, we have the generator matrix, because here we have to generate the code words. Same way we looked up the Galois field 2 to the 4. So we observe that we have 16 elements. So in this case, if we have to consider encoding using this as our code book, so it means that the code book will contain 16 possible code words, right? So we already know what the message bits will look like, okay? So the message bits are those 0000, 0001, right? 000, 0010, 0011. You get it? So these are going to be the message bits. Then we now figure out a way to add some redundant bits, okay? So B to the M, okay? So this could be either 000 or so, or so depending on how we design it. But we're going to use the polynomial to design it. So it means that this will now form first code word, second code word, third code word, fourth, to the 16th, okay? To the 16th code word. Now, once we have that, or code vector, as you may call it. So once we have this generated, then we'll now use the parity matrix, this is G, H, to decode using the same code book. Is that clear? Hope you are with me.
Yeah, yeah.
Okay.
Yes. So
okay. Yeah, I didn't get that. We're going to say something. Okay. And then if we have to adopt the extension field 2 to the 3, then we know we have 8 elements, okay? So it means the code book will contain 8 possible code words. So our generator matrix will also work with those 8 code words to generate our code words for transmission over the channel, while we use the parity matrix mapped to the 8 code words for decoding, okay? So we are going to play with all of those as we progress. But the bottom line is we've been talking about message symbol and that the information is contained in this message symbol. So the fundamental question now is, what is information? Okay? How do we describe this information that we are trying to say is in this message bits? So I think now I'll throw this open to the class for interaction. What is information? So over to you. So tell us, what is information? Okay, I have quite a number of, can Joel tell us what information means? I think he can unmute, yeah. Or he's not present. Is Joel here? Okay, how about Iyanu? Is Iyanu in class? Okay.
Oh, yes, I'm here, sir.
Okay, that's Iyanu, right? Okay,
Yes, sir.
Can you bail us out when we say information? Because we've been talking about, okay, the code word will contain the message bit and all of that. Fine, we've looked up the coding algebra, right? So, but what is information? Because we've seen that information is different from the message, right? We just mentioned that, well, if we have the message bit K, the information is contained in this message bit K or message symbol. So what is information?
Okay, I think that we could say the information could refer to as representation of data, whether encoded or encrypted, used to secure communications thereabout.
Okay, representation of data, whether coded or not, right? Okay, thank you. Beautiful contribution. So we need more contributions on this, okay? We need more contributions. So we need to hear.
Right, sir.
Okay, go ahead, Ibrahim.
Okay. All right. I think information is based on the first class. What I gathered there, we could define the information to be measure of uncertainty associated with transmitted message.
Okay, measure of uncertainty associated with the transmitted message. Okay, so any other contribution? Thank you so much. So any other contribution?
Yes, sir.
Go ahead, please.
Yes, sir.
Yes,
I would say information is simply the content of that transmitted message.
Content of the transmitted
message.
Beautiful. So do we have any other contribution? Any other contribution? I'll suggest feel free to air your views, okay? You never know how much we'll learn from your contribution. Okay?
Collection of data.
That's vulnerable.
Yes.
That's what? Information?
Yeah, it's collection of data.
Collection, right?
Yeah.
Collection
of data. Transmitted.
To be transmitted, right?
Yeah. Yes, sir.
To be transmitted. Beautiful. These are beautiful contributions. Okay, so I think we can work with these. We have representation. We have it as the representation of data, whether coded or not. Okay. Then we have it again as the measure of uncertainty associated with the transmitted message. Then we also have it as content of the transmitted message. This is pretty smart because we said the information is contained in the message. So it's the content of the transmitted message. Then collection of data. It's a collection of data to be transmitted. So the fundamental question arising from the first contribution and the last contribution is, what is data? What is data? So who can help us out on that? What is data? What is data?
Yes, sir. From let me say ancient definition, data is raw facts or unprocessed information.
Raw facts or
unprocessed information.
Data is raw facts or unprocessed information. And now when we have information, the bottom line is data is also information, right? Yeah.
Yes.
It's also information. So we cannot decide at what level are we trying to describe this information. And here we have another keyword, coded or not. So meaning this definition is consistent with the so-called ancient definition we're just given, right? Like you said, ancient. So why did you say ancient?
It's a definition we've known maybe from primary schools and all that.
Okay. That sounds good. So it means whether coded or not simply talks in terms of raw, right? So we're trying to we're trying to validate all that have been said. And then a collection of data to be transmitted. So that's why content of the transmitted message. Beautiful. Now, this is where we now have to draw some basic idea. Okay. Now, when we say information, from the information theoretic perspective, we are actually trying to measure uncertainty. And how do we quantify uncertainty? Okay. Now, if we come back to our binary vector space, where we have the possibility of having a 0 or a 1, which brings us to distribution of bits. So it means that it is either we receive a 0 or we receive a 1. And with respect to certainty, uncertainty, this can move from the point of 0% mapped to some point of 100%. Not now, I'm now talking not in terms of the data transmitted, in terms of the measure. Okay, in terms of the measure. And like I said in our last class, if you know what I want to transmit, can we say information have been passed across?
No.
So it means that the more you know about what I have to transmit, the less information is passed. So how do we validate this? If information is the measure of uncertainty associated with this message. So it means that for each message symbol, there's a probability of occurrence associated with it. Okay? Sorry. Okay? And now, if that is true, then it means that information may be described as the logarithmic function of the inverse of the probability of occurrence, which is the same as negative log base A pk. Okay? Now, this base determines the unit. So if A is 10, we say it is Ban or Hartley or Hart. If it is 2, it is bits. If it is base E, it is natural logarithm nav. So, but we are working in base 2. Now, let's assume, what is the logarithm of 1? The logarithm of 1.
0.
Is equal to 0. So the information contained in the message will be 0 if it is certain, if the probability of occurrence is certain. If we are sure that it is going to occur, the event is going to occur. But what if it is less than 0? Then, then it will occur, okay? So it means that if the probability of occurrence is certain, it's 100%. So it means there is no uncertainty. Then no information is passed. So you now see that for us to be able to vary the amount of information contained in the message symbol, then this mathematical tool forms a basis for our description. So hopefully in subsequent lectures, we'll try to go into the mathematics of describing this information content or contained in the message. Because in every write, we want to be able to extract the information from the received message sequence at the end of the day. Okay? Okay. So I think this is a good place to stop from my end. So any question, please? Any question?
No question from here, sir.
Okay, no question from here. Okay.
Thank you, sir.
So I think we are just in time. We'll see you in our next class then. So bye.
Thank you, sir.
Thank you.
All right, thank you, sir.
You're welcome.
Thank you, sir.
What about attendance?
I will look forward to seeing this note on your channel. Thank
Fine.
you, sir.
I'll try to upload it as soon as possible.
Attendance.